All right, welcome back to the second half of Adam's tutorial talk. So I won't waste any of his time and I'll just start things off. I will say at the end, when it's time to ask questions, I'll hand you the mic just so that it's abundantly audible for everybody who's watching. All right.
Okay, thanks, Guy. Can everyone see my screen?
Yeah.
All right. So let me just finish up with a couple slides from the first hour, and then we'll head right into part two. If you recall, sort of the main point of the first hour was studying this question: can we find algorithms that go beyond the CSQ model or can do things that gradient descent can't do? And we looked at this filtered PCA technique as one way of doing that. Now, there's another way that we could move beyond the CSQ model, and that is we could run gradient descent on some very strange loss function. So the CSQ lower bounds hold if you're running gradient descent on your usual loss functions like square loss or logistic loss. But if you cook up something very strange, then for technical reasons, I can't necessarily prove the CSQ lower bound. In particular, there's a paper by Gay Lee Ma that shows how to learn one hidden layer neural networks. And again, it requires sort of positivity of the coefficients and condition number bounds, but it simulates these tensor decomposition algorithms by running gradient descent on a carefully chosen loss function. They call this landscape design. So you're choosing the loss function in a strange way. So it's suggestive that perhaps there's a whole range of techniques that we could apply to come up with very interesting and novel loss functions to get around the CSQ lower bounds. So let's consider just the case of one activation. I know already we were looking at these cases of one hidden layer. I'm going to make the problem even simpler now. I'm just going to assume that the conditional mean function expectation of y given x is actually phi of w star inner product x for some hidden weight vector w star, and phi again could be rel u or sigmoid. In this setting, it could be any Lipschitz monotone activation. Okay, then if you look at the associated optimization problem, which is you're trying to find the min over w of the square loss expectation of the true square loss expectation of y minus phi of w dot x squared, it's not too difficult to see that this is a non-convex optimization problem because you have this sort of minus phi inside of a square. And this is non-convex. Still, it turns out that finding a w that minimizes this non-convex loss is solvable efficiently in polynomial time. And this was first observed, well, I guess there was sort of a predecessor paper by Kalai and Sastry, and then it was sort of all worked out by Kakade, Kalai, Kanade, and Shamir. And the algorithm that they used, or that they called, is something called GLM-tron. It's like the perceptron algorithm, but so it's a simple iterative update rule. But it actually finds, it actually finds a w prime such that phi of w star dot x is close to phi of w prime dot x. So you can actually solve the case of one activation, and it works for all marginal distributions on x, not just the Gaussian distribution. So it's a nice primitive to have. And even before that, I think maybe it's the late 80s, there's a paper by Auer, Herbster, and Warmuth, could be the early 90s, I can't completely remember, where they introduced this notion of a matching loss. Okay, so you can take any phi that's monotone in Lipschitz, and they introduce this loss. So you have some candidate w, and you want to know how good is w? Well, they associate a loss function, calling L sub d sup s here, and it's the expectation over xy of the integral from 0 to w dot x of the activation phi minus y so integrated over that range. So if you want to know what the loss is according to this matching loss for a particular weight vector W, then you need to integrate the activation over the range 0 to W dot X. And what you can prove is that if phi is monotone in Lipschitz, oh, I see I already had it written there, then this loss is actually convex. And furthermore, if it's L Lipschitz, then what you can prove is that the square loss is at most L times the difference in losses of the surrogate loss. One way to sort of see this geometrically is just to notice that if you have any monotone increasing function and you integrate it, it's easy to see the integral is going to be convex. Why will the minimizers be within L of the minimizers of the surrogate loss? Again, you have to draw a picture and you can show that the function has to always stay above this slope L line if you draw the graph. Okay, so this is a very nice observation. It sort of explains why that GLM-tron algorithm works. And it has some nice applications. So with Serbi-Goel and Raghu-Meka, we used this loss to come up with an efficient algorithm for learning one-layer convolutional nets. And I think a very kind of interesting open question is, is there some type of surrogate loss for one hidden layer ReLU networks? Could it be the case that you can come up with a very novel loss whose, say, local minima correspond to the global minimum of the original one-layer neural network learning problem? I don't, to me, this is a very underexplored area of research. I just don't know the answer to it. There's a very kind of nice theory about this matching loss but it only holds sort of for one activation. So it's to be determined. Okay, so this is the end of part one, although we'll get back to matching losses in just a second. So let me start the second part of my talk. Let's see. Good, okay. So for the first part of the talk, we were talking about supervised learning problems. I'm a big fan of supervised learning. For most of this talk, we'll be looking at unsupervised learning. So I know that Guy and Salil will be very happy. In the unsupervised setting, we don't have labels. We just have, in this case, a distribution, some unknown distribution on -1, 1 to the n. And think of n as sort of the number of features that you have in your data set. And we get IID samples from D, and we want to learn something about the distribution, some structural property of the distribution, or approximate it in some type of distance. For this talk, we're going to be trying to approximate the dependency graph of this distribution. So what is a dependency graph? So if you fix a distribution on -1, 1 to the n, then you can come up with a graph on n vertices. And this graph encodes the conditional independence information about the distribution. So the way that we put edges in this graph is, if I look at any vertex I and I condition on any values of i's neighbors, then the value xi should be independent of the remaining vertices. Okay, so for any distribution that you give me, there is some corresponding dependency graph. It could be the complete graph. I mean, everything could be completely dependent on everything else. It could be a tree. It could be complete. If there are no vertices, then everything is completely independent and uniform. But the graph does encode conditional independence information. It tells me, again, if for any vertex I, for any feature I, if I condition on all the neighbors in this graph, then I'm independent of all the values of every other vertex in the graph. And the goal here, the learning problem, is very simple. You're given draws from this distribution D, and you just like to figure out what are the edges in this graph. I just want to understand what's the conditional independence structure of all the features in this distribution. So what are the edges in this graph? And of course, I'd like to do it using as few samples as possible and as quickly as possible. And so this is also called structure learning. So here's the brute force algorithm. We're going to want to try and do something smarter than this. And that is, well, I start with an empty graph on n vertices, and I want to figure out for vertex I, what's its neighborhood? So I'm just going to enumerate over all possible neighborhoods. And if it's a degree D graph, well, then it'll take time n to the D. And for every neighborhood, for every candidate neighborhood for a vertex I, I'll choose enough samples so that I can look at some elementary statistics. So I can see, well, is this vertex conditioned on, here's my candidate neighborhood. I'm going to take a bunch of samples and then, conditioned on the values in this neighborhood, is I here really independent, just by checking some simple statistics, is I independent of the rest of the vertices in the graph? And that way, I really can figure out what all of the neighborhoods are for all the vertices in the graph, and I'm done. Of course, it's not the most exciting algorithm, and this is something that we want to do better than. So there's a very classical and nice result from the 70s by Hammersley and Clifford. And it's a way to relate the dependency graph to the PDF of the distribution. It's a very nice structural property. What it says is that if you have a distribution D and you look at its underlying dependency graph G, then the PDF factorizes as a product of cliques in this graph. So that is to say, the probability that Z equals some string little z is the product of some function over all cliques of just some function of variables within that clique. And an immediate consequence is that I can write the PDF in this relatively simple form, that the probability that Z equals any bit string little z is proportional to exp raised to the power sum over all, here I've written t cliques of phi of I of z. So phi of I is just some function of the variables in this clique of z. And if all of the cliques in this summation are of size less than or equal to t, then by definition, we call this distribution a T-MRF. Okay, so it could be that the T cliques are very large and that you have an MRF of very high order, or it could be that your cliques, that the PDF only depends on cliques of size 2, namely edges, in which case we call those distributions Ising models. Okay, so these are called Markov random fields of order T. They factorize in this very, very nice way. And as I said, one particularly important class of distributions that we're looking at are Ising models. And those are the distributions where you can, the PDF is proportional to exp of the sum over all edges in your graph, a weight, Wij times Xi Xj, plus something called the mean field, which is just some theta I Xi, some linear combination of your vertices. Okay, so if your cliques if the PDF factorizes into cliques of size 2, then we call it an Ising model. And the weights on the edges really do encode this PDF. So it's just a simple way of writing the distribution. So what is the sample complexity for learning general Ising models? This is from a recent paper of Devroy, Mehrabian, and Rudad. And what they proved is that if you have a general Ising model with m edges and n vertices, and you take k samples, then the minimax rate for learning with respect to total variation distance is theta of m plus n, theta of square root of m plus n over k. And as far as I know, there's no efficient algorithm known that goes along with this sample complexity bound. Okay, now the thing is, I think this is actually an interesting problem, come up with some type of efficient algorithm to complement this bound. But we're not super interested in general Ising models. And the reason why is that if I have a graph, say the complete graph, and I discover that my dependency graph is the complete graph, well, I haven't learned that much about my features. Sort of just tells me, you know, everything's dependent on everything else. Sort of not the most exciting or illuminative case for the distribution. So a measure of complexity that we'll take for these Ising models is that we're going to consider Ising models that have bounded degree. Okay, so we'll assume that the degree is bounded by D. You can think of it as a constant if you'd like. And then it turns out that this is the result of Santhanam and Wainwright. That in the case when you bound the degree of your Ising model, then the optimal sample complexity that you can hope to achieve is roughly 2 to the D times log n over alpha, where alpha is a lower bound on the absolute value of the edge weights in this graph. More generally, if lambda is sort of the sum of the absolute values of the weights for an upper bound for any fixed vertex, so sum of the weights of a neighborhood, then you can obtain a bound 2 to the lambda log n over alpha. Okay, and this is sort of a more interesting setting because it means that the graph is pretty sparse. And I'd like to use just, you know, if you think of D as a constant, I'd like to figure out the conditional independence information using only sort of order log n samples for the graph. So with very few samples, I'm really quickly getting a lot of information about how my features interact with each other. So that's sort of been the standard way of considering structure learning for Ising models. And as I said, there are actually a lot of applications for structure learning. I mean, the one that's frequently cited is when you're trying to understand protein-protein interaction networks in biology. There are many connections to statistical physics and also to learning kind of the Hamiltonian in quantum computing. It's related to this problem, sort of the quantum version of this problem. And structural learning has been around since the 60s when there was a result due to Chow and Liu that discovered the dependency graph when you're, in the case when the graph is a tree. Okay, so let me tell you about some other prior work for learning the dependency graph of a bounded degree Ising model. So typically what happened, you know, kind of 15 years ago, is that various additional assumptions on the graph were taken, i.e., you know, two things that I've brought up here are something called correlation, the correlation decay property, sort of measures how correlated your features are as their distance grows within the graph. So there's an algorithm for learning Ising models by Bressler, Mussel, and Sly under that assumption. And then there's an approach by Ravi Kumar, Wainwright, and Lafferty that assumes that not only is your distribution coming from the Ising model, but it satisfies sort of an incoherence assumption related to the incoherence assumption from compressed sensing, but different. And then there was a very influential paper by Guy from 2015 that finally, you know, gave an algorithm for structure learning Ising models that did not take any of these additional assumptions. So it worked for general degree D Ising models, but the sample complexity was 2 to the 2 to the D times log n over alpha to the 4th. And so instead of getting sort of the correct single exponential bound on the sample complexity, it was getting a doubly exponential bound on the sample complexity. And then there's a nice paper by Hamilton, Kohler, and Moitra that extended Guy's result to the case of higher order MRFs. And both of these results use greedy algorithms. So they define a notion of mutual information between two vertices in the graph. And then they use greedy algorithms to kind of construct the neighborhoods for the vertices. Okay, so before I tell you how to get the optimal bound, let me just remind you what the sigmoid function is. Maybe this comes sort of out of left field, but remember that the sigmoid function is an activation that we sort of mentioned in the last hour that I didn't even bother to define. But it's this function 1 over 1 plus e to the minus z. And keep in mind, it's monotone and also 1 Lipschitz. You know, it goes to 0 on the left-hand side and goes to 1 on the as you go to the right-hand side. And if you're really cool, then you work with tanches instead of sigmoids. Like Fred Kohler always tells me, it shows my age that I call these sigmoids and not tanches, but whatever. If you want to think of them as tanches, you can. Okay, so I want to show you how to learn graphical models or these Ising models using a neural network approach. So I want to use tools from supervised learning to solve this problem because I'm preferential to supervised learning. So let me show you how you would do that. So again, the PDF of an Ising model has this nice form. It's proportional to the sum of the weights, zi, zj, and then theta I, zi. And now I'm just going to switch, doesn't really matter, but I'm going to switch from -1, 1 to the n to 0, 1 to the n. So I'm going to switch from the variable z to the variable x. And I'm going to pick one vertex, say vertex I in my dependency graph. And I'm going to assume that that is my label because we're going to do supervised learning. So xi is going to be my label, y. And then I'm going to condition on the rest of the variables. That's how I've written x minus I. That means all of the values of the variables except for I. Okay. And it's not difficult to prove because we have this nice form of the PDF. You know, it almost looks like a sigmoid. Just do a little manipulation. It turns out that the conditional distribution of y given x minus I is actually equal to a sigmoid of w dot x minus I plus theta. Okay, so we're back in this case of where we're learning sort of a generalized linear model. The conditional distribution is just a single activation. And if I could learn this W, well, that W encodes all of the neighborhood information for vertex I. So if I could learn this W, I would just have the neighborhood for vertex I. And then I could repeat this for every vertex in the graph, and I would just get all the neighborhoods for all the vertices in the graph. Problem solved. Okay, so why don't we do just that? Let's view this as simply as a problem of learning a generalized linear model, just learning a single activation. And we'll run glmtron from, well, I guess it was the beginning of this talk, to learn W, and we'll just read off the edge weights. Well, there are two problems with this. And the first one is the bigger problem. So problem one is that glmtron uses omega 2 norm of W samples. So this is always going to be like n. And remember, we wanted to learn the dependency graph with optimal sample complexity. We wanted to do log n samples. And if I just run glmtron, I'm going to pay n in the sample complexity. Okay, so I'm in trouble there. Now, the other issue is that if you run glmtron, it doesn't find W per se. It just finds a W prime such that the sigmoid of W dot x is close to the sigmoid of W prime dot x. So once you put them inside of a sigmoid, they're close, but we're not actually getting parameter recovery, which is what we really need to do if we want to do structure learning. But I think this is another nice example of why it's important to study even very simple neural networks. Just, even learning a neural network with one activation can do very sophisticated things. It can get you algorithms for doing structure learning for all, graphical models, undirected graphical models. Okay, so instead of running glmtron, in 2017, Raghu and I came up with this algorithm that we called sparsitron, in homage to glmtron. And the algorithm is as follows. Here's at a high level what the algorithm does. You're given a bunch of examples, x1, y1 through xt, yt, and you have the guarantee that the conditional distribution of y given x is, again, equal to sigmoid of w dot x. And it does exactly what glmtron does. It outputs W prime such that they're close in square loss. But instead of using a two norm, instead of getting a two norm bound on the hidden weight vector, it only uses a one norm bound times log n over epsilon squared. So there we're getting the log n, and the one norm bound is a proxy for the sparsity of the graph. So that's the parameter regime that we wanted to work in. And so this is the algorithm that we developed. I couldn't tell, was there a question from the audience? I heard some mumbling.
I was just asking if log n really comes from being log 1 over delta, where delta is the probability of failure, and then you'll do a union bound over the n things you're learning.
Oh, you'll see where it comes from. I mean, not really. There's another log 1 over delta because of that, but you can kind of massage it away. Okay, so how does this algorithm work? Well, we use a best experts approach. So we're going to use this very classical and old theorem, very beautiful theorem of Freund and Shapiro from '89. And in their setting, you have these experts, E1 through En, and it's an online learning problem. So in each round, each expert is trying to predict something. I don't know whether it's going to rain tomorrow or not. So each expert outputs a value 0 or 1. And associated with each expert is a weight, W1 through Wn. And initially, all the weights are the same. So you start with sort of a uniform distribution on your experts. You don't know which expert is good, which expert is bad. But at each round, at each time t, they're making predictions. We can start to see how good their predictions are. And at each time t, depending on what their prediction is, they suffer a loss vector, L sub t. So each expert suffers a loss. These are arbitrary values. These losses are arbitrary values in 0, 1. And then Freund and Shapiro in '89 gave this algorithm hedge that updates the weights of the experts according to the loss that they suffered. And the weights have the following very nice property. If you look at the sum of all the weighted losses that you accumulate for capital T rounds, then the weighting system has this very nice property that the sum of the weighted losses, so sort of in aggregate, is at most the loss of the best expert, so minimum over J, of the sum of the losses of the best expert, plus root T log n. So here's really where the log n is coming in. So as you know, this weighting scheme has this very nice property where, as you aggregate all of the weighted losses of all the experts in time, you're doing as good as the best experts' losses plus only root T log n. So if you divide by T, then you're getting that term is vanishing. So this is the approach that we're going to take. So our experts here, so remember, we're really trying to predict what's the value of xi. We're trying to understand its neighborhood. And this is the kind of the label. So we're trying to predict this label. And our experts, you can think of as just the other vertices in the graph. And so every time I take a draw from the distribution, I have a label, which is xi. And then I have you can interpret the other values of the vertices in the graph as a prediction for what xi's label is. So initially we you normalize your current weight value, and then the loss, so the real choice that we have when we're applying this Freund-Shapiro algorithm is how are we going to choose the losses? I mean, they give their algorithm specifies how you update the weights. The only real choice we have here is how do we update the losses? But you can kind of imagine vertices that are agreeing with y shouldn't be penalized, and vertices that are disagreeing with y should be penalized. And so we're hoping that we can kind of hone in on the neighborhood of vertex I. And so it turns out that the loss function that we suffer, what you should choose is exactly that. You should choose sigmoid of the current weights times the vector of the experts minus there should be a thing here, minus the y value. And then you multiply that by the vector x minus I. Okay, so we're really updating each expert by how much kind of the sigmoid of their prediction differs from the y value. And why does this, why? So there are kind of two reasons to see sort of why this works. One, first of all, you can just stick it into the Freund-Shapiro hedge algorithm, and you'll get a regret bound that you need. But why doesn't this work for, say, all activations? Where are we using the property of sigmoid here? Well, it turns out that as you work through the analysis, at some point you end up with a quantity a minus b times sigmoid of a minus sigmoid of b. And then we use the Lipschitz property of the sigmoid activation to show that this is less than or equal to sigmoid of a minus sigmoid of b squared. So that's really where we're using sort of the Lipschitzness of the activation. But another reason to think that this might work is that this quantity, sigmoid of w dot x minus I minus y, this is actually the gradient of the surrogate loss, of the matching loss for this type of generalized linear model. Okay, so another way to think of this is that you're doing kind of, that these multiplicative weights are doing a type of stochastic gradient descent. And indeed, this corresponds to a type of mirror descent.
Is it possible? I mean, okay, so what you're doing is sort of like simultaneously designing some convex problem and the algorithm to solve it. Is it possible to just set up a convex problem for this and then black box the, throw it into whatever convex optimization solver you want? Like, is there some underlying convex problem that I can see?
Yes, so there are two answers to that. Well, let me get back to that in a second. Yes, you can just minimize a particular convex loss. Just one second, I'll tell you about it.
Okay, thanks.
Okay, so now part two is, we ran this Parsotron algorithm. We got some W prime. The expected square loss is close. We actually have to show how to figure out that we can recover, how to recover W prime from W. And if you remember the sparsitron analysis, it only paid the one norm of W log n over epsilon squared. And now in order to get parameter recovery, this is where we end up paying 2 to the one norm of W times log n squared. You have to sort of show that if you make this small enough, then because the sigmoid activation is sufficiently anti-concentrated, although it's not very anti-concentration near the origin, that you can actually get parameter recovery. I don't want to go too much into it because it's a little tangential to the other points that I want to make in the talk. But if you want to learn higher order MRFs and not just Ising models, then you need to use some higher order facts about anti-concentration of polynomials. Again, this is only to go from the square loss of the GLM being small to actual parameter recovery, but you can do it. And so the bottom line is that if you do this, you'll get the nearly optimal 2 to the d times log n sample complexity. And you'll also get a nearly optimal running time of order n squared. There's a reduction to the light bulb problem, which is sort of a kind of like a parity with noise type problem. So you can't, if you believe that that's a hard problem, you can't hope for better than n to the 1.63 or something. I forget exactly what it is, but we get running time order n squared. And as I said, it's an online algorithm that will work for all higher order MRFs. If it's an order T MRF, then your running time becomes sort of n to the t, and your sample complexity becomes sort of 2 to the dt. Now, unbeknownst to us, while we were doing this, there was a result that had appeared just a year earlier by Vufre, Misra, Lokov, and Chertkov, again, just for learning Ising models. And it did get the correct 2 to the d times log n sample complexity bound. But the running time was order n to the 4th. And the reason for that is, as Sam suggested, they came up with a non-standard convex optimization procedure and used general purpose tools for convex programming to kind of find a solution. And so they ended up with sort of a suboptimal running time. But but they did have the idea of kind of minimizing some convex objective. They call it the interaction screening objective. Okay, and there have been several extensions of this work. There's a nice paper by Wu, Sangavi, and Demakis that showed if you don't want to run this multiplicative weight update algorithm, you can run something called, you can just run L1 regularized sparse logistic regression instead. That will also work. And then again, Vufray, Mizarov, Lokov, and Chertkov later showed how to reinterpret kind of this it's sort of well known that the correspondence between multiplicative weights and mirror descent, but they gave a full mirror descent implementation to obtain the correct sample complexity and runtime bound, and also give some generalizations to for other types of undirected graphical models. And if you're interested in noise tolerance, there's a paper by Serby and Dan Kane and myself. But I think there are kind of two interesting challenges that present themselves after studying this problem, because in the case of Ising models or Markov random fields, all of the variables that you're looking at are observed. You see there are no hidden variables. And there's sort of two directions you could go from here. The first question you could ask is, okay, well, how do I learn undirected graphical models when there are latent variables? So these are so-called Boltzmann machines. And the second way you can move is, well, I want to handle the case of continuous values on my vertices. What if the vertices are Gaussian, and I have some sort of arbitrary precision matrix, including my Gaussian? How can I learn the precision matrix? These are the so-called Gaussian graphical models. Both are very interesting lines of research. Just in order to fit in with what I talked about in the first hour, I decided not to talk about Gaussian graphical models, but I would like to move in the direction of Boltzmann machines. So I'm going to spend the rest of the time talking about learning with latent variables. I think that it's a very important challenge. Okay, so let me define a graphical model with an undirected graphical model with latent variables, probably the simplest model that you could think of. This is something called a restricted Boltzmann machine, or RBM. And I like to think of it as just it is just a bipartite graph. And the X variables on the left-hand side, those are your observed variables. And the variables on the right-hand side, those are your latent or unobserved variables, Y. There are typically N variables that are observed and M variables on the right-hand side that are latent. And then again, we have this nice decomposition of the PDF so that the joint distribution over X and Y is proportional to some exponential on X transpose capital JY plus H transpose X plus L transpose Y. And this J is the interaction matrix. And you can see that there are no edges among the observed variables and no edges among the latent variables. And we're only observing the X's. So, what we'd really like to, the learning problem here, what we'd really like to figure out is the two-hop neighborhood of vertices on the left-hand side. So if you were to literally square the adjacency matrix of this graph, you'd like to understand what the neighborhood is of the observed variables. And restricted Boltzmann machines have been around for decades. I think that understanding and uncovering latent variables, or being able to figure out the kind of two-hop neighborhood of the observed variables when there are unobserved variables, I think more and more people are realizing this is sort of a fundamental obstacle to succeed if you're studying causal inference. There've been a lot of applications in collaborative filtering and dimension reduction. You can stack them to form something called a deep belief network, which is a heavily studied type of generative model. And as we'll see, there's some interesting relationships to neural networks. So I think this is learning RBMs is sort of the frontier for learning graphical models from the perspective of developing provably efficient algorithms. Right. So as I said, just given the observed variables, the learning problem is to identify the two-hop neighborhood. or, if you want, technically the two-hop, we're interested in kind of the Markov blanket of the observed variables. So the two-hop neighborhood could be smaller than, the Markov blanket could be smaller than, strictly speaking, the two-hop neighborhood of the square of the adjacency matrix, but let's not worry about that right now. And so the question is, what can we hope to achieve? Well, it turns out, and this was proved very recently in a paper by Bressler, Kohler, and Moitra, that every RBM, in terms of expressiveness, is equivalent to a TMRF, so an order TMRF, where T is the maximum degree of a hidden node. So it's not too difficult to see that if you give me an RBM and I marginalize out, so I just sum over the latent variables, that I will get a Markov random field. The other direction is quite a bit harder to show that for any Markov random field, I can construct some associated RBM. And that's what they prove in their paper. And they show that every order T Markov random field is an RBM of degree T, where you have order n hidden units, and there's some constants involving kind of the degree m here that I don't want to get into. And the reason why this is sort of bad news is that as an immediate corollary, you can show that KMRFs actually encode K-1 sparse parity with noise. Okay, so that means that if you believe that learning sparse parity with noise is hard, then learning RBMs, you can't hope to do better than n to the little o of k. So that's sort of a bummer. And so the approach that Bressler, Kohler, and Moitra took in their paper was to assume that the RBM was ferromagnetic. And basically what that means is the interaction matrix is non-negative. And their idea was to form this potential function, this discrete influence function that takes a set of variables S and outputs the expectation of xi conditioned on those variables all being set to positive. And what they proved in their paper using the Griffiths-Hurst-Sherman correlation inequality is that this discrete influence function is submodular. And furthermore, the maximizers of this discrete influence function actually contain the two-hop neighborhood of any vertex I. Okay, so they prove a very nice structural property, and that leads to a very natural greedy algorithm for learning the two-hop neighborhood. So again, recall we have this discrete influence function, and I can just, given xi, I can pick the variable xj that increases the discrete influence function the most. I can repeat that a bunch of times. And then after several iterations, they do some pruning to make sure the neighborhoods are all of the right size. They basically throw out variables that don't decrease the discrete influence function too much. And when you're trying to gather these statistics to maximize this discrete influence function, of course, you may need to pay sort of exponentially in the size of the neighborhood. And indeed, that's what happens. They basically, I'm kind of simplifying things. They basically get sample complexity 2 to the d log n and n squared running time, and this d2 is the degree in the two-hop neighborhood when viewed as an MRF. So, but you can think of it as just sort of 2 to the degree times log n samples and n squared running time. Okay, so that's great. And there in 2020, Surbi-Goa had a very interesting extension that generalized this to arbitrary external fields, as well as the POTS model for higher alphabets, using the FKG inequality and some properties of conditional covariance. Okay, so still the open question remains: how do we learn sort of general restricted Boltzmann machines? And we have to make some assumption, if you believe the hardness of sparse parity with noise. There was a paper by Bressler and Buhai in Europe's 2020 that gave an incomparable result to kind of what you would naively get by reducing things to an MRF, n to the 2 to the s, where x is the maximum number of latent variables connected to the MRF neighborhood of any vertex. But this sort of leaves open the question of sort of what's the right measure of complexity for learning restricted Boltzmann machines? I mean, they seem hard. Ferromagnetism was one way to go, but is there some other natural measure of complexity that lets us handle more general cases? So let me show you one possible approach. And again, this is taking a sort of a neural network approach to learning RBMs. This is from a paper with Serby and Fred. And if you recall, for Ising models, when we looked at the conditional distribution on xi given x minus I, we showed that this was sigmoid, or here for Fred, I've written tanh of W inner product x minus I. It's a very simple one unit neural network. You could ask, what does this conditional distribution look like for an RBM? Maybe it's a class of neural networks that we can solve. And so it turns out that you can start from this formulation of the PDF for an RBM. So this is for general RBMs. This is what it looks like. And if you condition on all of the variables outside of xi, then you'll see that the only quadratic terms that appear in this PDF are right here, xi times one of these yj's. Those are the only quadratic terms that appear after you've conditioned. What this means is that the conditional distribution actually is an Ising model. It's a star where xi is the root, and you have these yj's attached to it. And it's known from some techniques, applying some techniques from belief propagation, in particular, a result of Mazzard and Montanari, that whenever you have a tree Ising model, the conditional distribution can actually be computed using techniques from belief propagation. It's not easy, but what you find is that the conditional distribution of xi given x minus I, well, it's no longer just a one unit neural network. It's now a two hidden layer neural network. There's a tanh on the outside. Then there's some other terms that I'm ignoring, but importantly, there's a tanh kind of on the inside. And then the interaction matrix with the ith row removed appears times x minus I. Okay, and these are referred to actually as supervised RBMs, because again, you're taking a particular vertex I, you're assuming it's the label, and you're viewing it as some sort of complicated neural network in the other variables. Okay, but the point is that it is a two-layer neural network with some very strange applications. Still, if you assume that the infinity norm of x is bounded by 1, which we have in this case because we're looking at discrete values on the RBM, then you can actually try and learn this two-layer neural network using polynomial approximation. So we have a toolkit for learning neural networks when you have norm bounds on the inputs and the weights. And there are a lot of techniques that you can use for doing polynomial approximation on, say, for any distribution on the sphere. And we need to use these results because the distributions induced from these RBMs could be quite strange. And we also applied a result that sort of tanh-like activations can be very easily and well approximated. This is from a paper of Kohler and Rostesky. And so if you take kind of that two-layer tanh neural network and you assume that, well, we know the inputs are bounded, but if you assume that the weights are bounded, then you can get some non-trivial degree bounds for polynomial approximators for these function classes. And the bottom line is that if you assume that the ith column of your interaction matrix is bounded in norm by lambda, and say one norm by lambda, then you'll get a sample complexity that is exponential in lambda. So roughly 2 to the lambda, and the running time will also be n to the lambda. And so, if you're willing to make assumptions, kind of norm bounded assumptions on your RBM instead of assumptions on kind of ferromagnicity, kind of the structure of the RBM, then you can still obtain non-trivial algorithms by viewing them as neural networks and applying some polynomial approximators. And in this paper, we also give a bunch of matching lower bounds based, again, on parity with noise. In this paper, we also sort of show a reverse direction. If you want to learn a neural network and you treat the label, the label itself as sort of a vertex in some very complicated RBM, then you can use greedy type methods to learn the neural network by viewing it as an RBM. And again, there we need to use a ferromagnetic interaction matrix. Okay, so I wanted to state, and this applies to both of the talks for today, I wanted to give sort of a laundry list of open questions that I think are very interesting and would give us really new algorithmic tools for learning neural networks and graphical models. So the first question that's still open and I don't have any hardness results for would be to learn RBMs with just a constant number of hidden units. Do that in polynomial time. I don't see why that isn't possible, although I really don't know how to do it. Learn, and you can see kind of a relationship here, learn one layer neural networks with respect to a Gaussian distribution with a constant number of hidden units. That's also, as I mentioned last time, open, and I don't have any hardness results for doing that. You could try and learn sums, so non-negative combinations of k ReLUs in fully polynomial time in k and 1/epsilon, so try and beat the Dioconicus Kane bound. You could try and learn deep ReLU networks with biases. So a key structural property that we used in our fixed parameter tractable paper was that they were all homogeneous ReLUs, so we don't know how to handle the case of biases. And then there's also some interesting questions about smoothed analysis here. What is the right notion of smoothed analysis for one layer networks? There was kind of a lot of progress made on this front by this recent paper of Awasthi Tang and Vijay Raghavan, where they showed that if you can smooth the hidden weight vectors and use tensor methods, you will get sort of the best you could hope for running time bounds in some of the parameters, but you pay for it in terms of the smoothness parameter. So they've made some nice progress there, but I think it's still open. In terms of a smoothed analysis for learning an RBM or an MRF, there are lots of potential ways to define it. And since I don't have any positive results, it's not clear to me what the right notion of smoothed complexity is for an RBM, but that would be interesting to kind of develop algorithms in that setting. Then also, what other alternatives are there to Gaussianity for the neural networks? Can we learn with respect to distributions that are derived from, say, an Ising model? I think that would be very interesting. And finally, there's a whole other class of problems that are related to kind of neural networks and graphical models, and that would be learning generative models. So you could imagine that a random Gaussian seed is chosen, and then you see the output of some multi-output generative model, and you would like to learn that distribution. It could be in TV distance, or it could just be learning the structure of the neural network that's generating the distribution. The only result about this that I know along these lines is by Wu, Demakis, and Sangavi. And there they have a result that shows that if you have a distribution that takes a generative model that takes a Gaussian seed, and each output is literally the output of just one ReLU activation. So they could be different ReLU activations, but each output bit is the output of a ReLU. Then you can learn the weight matrix up to rotations. Yeah, so I'll stop here. I think I'm out of time anyway. And thanks, and take any of your questions.
Great, thanks, Adam. So any questions from the audience? No questions. I mean, I guess, Adam, you raised many interesting questions already. There's numerous open questions that people are already thinking about. Yeah.
So have you seen this work by Garvesh Raskuti in, I think, 2013, which was about learning autoregressive models, but on the hypercube. So the IID form of that is learning easing models problem. So there they use again L1 regularized logistic regression and on the logistic loss, but with the L1 regularization, and they get a similar rate, but in the more general setting of Markovian dynamics and observing a single trajectory of it. Have you compared that with the IID recovery results? Because that seems a bit older than the results you mentioned.
Yeah, I'm sure that they need an incoherence assumption.
Incoherence, okay.
Can you offer any insight on, like, if you take a one-layer neural net and you train it on MNIST, like, okay, you made all these structural assumptions, and the question is what's the right one or set of structural assumptions to make things easy. Like, can you validate any of these assumptions if you look at simple things you get from training? I don't know how many hidden units you want, but whatever. Like, can you validate these with some experiments?
Well, I didn't take any assumptions about the one-layer neural networks. I mean, I'm not sure what you mean there.
Yeah, okay. I guess I don't have. I mean, in the first hour, for instance, we were talking about like non-negative weights or incoherence assumptions on the W's, like for the neural net part of the talk.
Yeah, I think when nobody's training one-layer neural networks on ImageNet, but certainly you get negative weights when you train typically for a lot of these data sets. I mean, and as you say, you also are typically over parameterizing. So the condition number of that matrix is going to be bad typically. That's really why you'd like to get rid of those assumptions. Sorry, I don't have a better answer for you.
Oh, no worries.
One more question here in the back. I'll take a second to bring the mic over.
Thanks, Adam. If I understand correctly, most of the, maybe not all of the results were in the identifiable situations. I think all the graphical models, but maybe not all the neural nets. So I guess there's two questions. One is, can you maybe highlight which of the results were also when in non-identifiable situations? And second, can you comment on whether you think the techniques and idea can carry over to non-identifiable situations?
Yeah, hey Nazi, thanks for that question. I think that there are a lot of results depends on if you sort of how bad the noise model is, whether it's agnostic or p-concept or, I could do a whole nother hour on just what happens with noise. So there are some things you can say. I would say in the, for graphical models, the noise model that we looked at was for Ising models, was that each vertex is independently, say, missing or flipped with some probability p. And it's kind of known that if you don't know, for example, if it's flipped, but you don't know the probability p, then there are hardness, like it's not identifiable. So there's some issues there. There've also been kind of two recent papers that show how to adapt to the Chow-Liu setting to noise to kind of find the best fitting tree-based graphical model. But I would say for one hidden layer neural networks, in harsh noise cases, like agnostic noise cases, I think you can prove a bunch of hardness results. For a single, even for a single activation, that turns out to be a very interesting question. For other noise models, like if you just know something about, if you have mean zero noise, let's say, then you can say, for example, all of our deep ReLU network stuff will work if you have mean zero noise. So it really depends on the noise model, but yeah, I mean.
Well, also for the RBM results, it's not identifiable, but your criterion for recovery is somewhat different to go around that, right?
Yes, right. We have to make a different assumption there.
There's a mix of different style of results depending on which circumstance one is in. All right, well, we're coming up upon the lunch hour, so maybe we'll end questions there. And of course, feel free to interact with Adam. He's a participant, and we'll be happy to interact and answer questions by email or Discord or whatever.
I'll also be there later in the semester in person.
Oh, great. Okay, so we look forward to your actual physical appearance. So thanks very much, Adam, for a very stimulating couple of hours of talks. I think you've really highlighted a couple of kind of directions where there's quite a bit of uncertainty and open questions and a lot of things to investigate. So in the afternoon, we'll kind of zoom in and get a sort of detailed view about how do you think about that boundary between what's possible and what's not possible, and what tools do we have to think about that. So enjoy your lunch and look forward to seeing you here in just under 2 hours. Thanks again, Adam.